Hello everyone, today Alex and I are here to present to you Chapter 12, Power System Controls. Here's an overview of today's lecture. We're going to go over generator voltage control, turbine governor control, and load frequency control. Here we have a steam turbine generator. This turbine governor shown in figure 12.1 adjusts the steam valve position to control the mechanical power output PM of the turbine. When a reference power level Pref is raised or lowered, the governor moves the steam valve in the open or closed direction to increase or decrease PM. The governor also monitors rotor speed omega m, which is used as a feedback signal to control the balance between PM and the electrical power output PE of the generator. Neglecting losses, if PM is greater than PE, omega m increases. The governor moves the steam valve in the closed direction to reduce PM. Similarly, if PM is less than PE, omega m decreases. The governor moves the valve in the open direction. Generator voltage control. The exciter delivers DC power to the field winding on the rotor of a synchronous generator. For older generators, the exciter consists of a DC generator driven by the rotor. The DC power is transferred to the rotor via slip rings and brushes. For newer generators, static or brushless exciters are often employed. Static exciters. AC power is obtained directly from the generator terminals or a nearby station service bus. The AC power is then rectified via thyristors and transferred to the rotor of the synchronous generator via slip rings and brushes. Brushless exciters. AC power is obtained from an inverted synchronous generator, whose three-phase armature windings are located on the main generator rotor and whose field winding is located on the stator. The AC power from the armature windings is rectified via diodes, mounted on the rotor, and is transferred directly to the field winding. Generator voltage control system block diagrams, developed by the IEEE Power and Energy Society beginning in 1968 and most recently in 2005. The IEEE Type 1 exciter is shown below in figure 12.3. It uses a shaft-driven DC generator to create the field current. The leftmost block represents the delay associated with measuring the terminal voltage Vt, where S is the Laplace operator and Tr is the measurement time constant. If a unit step is applied to that block, the output rises exponentially to unity with time constant Tr. The measured generator terminal voltage Vt is compared with a voltage reference Vref to obtain a voltage error delta V, which in turn is applied to the voltage regulator. The voltage regulator is modeled as an amplifier with gain Ka and a time constant Ta, while the last forward block represents the dynamics of the exciter's DC generator. The output is the field voltage EFD, which is applied to the generator field winding and acts to adjust the generator terminal voltage. The feedback block in figure 12.3 is used to improve the dynamic response of the exciter by reducing excessive overshoot. This feedback is represented by SKF over 1 plus STF, which provides a filtered first derivative negative feedback. For any transient stability study, the initial values for the stable variables need to be determined. This is done by assuming that the system is initially operating in steady state and recognizing that in steady state all the derivatives will be zero. Then, by knowing the initial field voltage and terminal voltage, all the other variables can be determined. For wind turbines, how their voltage is controlled depends upon the type of the wind turbines. Type 1 wind turbines, squirrel cage induction machines have no direct voltage control. Type 2 wind turbines are wound rotor induction machines with variable external resistance. While they do not have direct voltage control, the external resistance control system is usually modeled as a type of Type 2 wind turbine REXT control system. The block diagram for it is shown in figure 12.4 above. The purpose for this control is to allow for a constant power output from the wind turbine. For example, if a wind gust were to cause the turbine blades to accelerate, this controller would quickly increase the external resistance, flattening the torque speed curve. Similar to synchronous machines, the Type 3 and 4 wind turbines have the ability to perform voltage or reactive power control. Common control modes include constant power factor control, coordinated control across a wind farm to maintain a constant voltage at the interconnection point, and constant reactive power control. Figure 12.5 shows a simplified version of a Type 3 wind turbine exciter in which QCMD is the commanded reactive power, Vt is the terminal voltage, and the output, EQ is the input to the DFHE model. For fixed reactive power, QCMD is a constant, while for power factor control, QCMD varies linearly with the real power output. Generator voltage control system block diagrams. Block diagrams such as those shown in Figure 12.3 are used for computer representation of generator voltage control in transient stability computer programs. In practice, high-gain, fast-responding exciters provide large, rapid increases in field voltage (EFD) during short circuits at the generator terminals in order to improve transient stability after fault clearing. Equations represented in the block diagram can be used to compute the transient response of generator voltage control.